Hi, in this lesson, I want us to look at the history of life on Earth. Nothing too ambitious, but we are going to focus on about the last 600 million years or so. In particular, I want us to look at the theories around some of the major extinction events, because the history of life on Earth is punctuated by major episodes of extinction. And those extinctions have driven the evolution of life as we know it today on Earth. Without those extinctions, we wouldn't have seen the same degree of evolution that we can see evidence for all around us. In particular, I want to look at some of the geological evidence for these extinctions. For this lesson, you're going to need your History of Life handout. There may well be a colour sticker of a graph to put on there. Okay, let's go. This is Sepkoski's graph. For those of you that did GCSE, you'll have seen this graph a couple of times before. It's probably the one piece of data that keeps cropping back up as we make our way through the various levels of geology courses. It's an important graph because it shows us the changing diversity of marine life, marine invertebrate life, to be more specific, over geological time. Now, it does this in a number of ways. It plots as a vertical axis there the number of marine families. Now, a family is quite a big taxonomic group that will contain possibly many different genera, possibly hundreds or thousands of different species. So, they're quite large groups. But we do see some patterns of how they've changed over time. Now, Jack Sepkoski, who put this graph together, divided up these marine invertebrates into three different groups. Firstly, what he called the Cambrian fauna, dominated by the trilobites, and these were the small shelly fossils that evolved very rapidly during the Cambrian explosion. Most of these animals were sort of bottom dwellers on the sea floor. You can see the Cambrian fauna evolved rapidly through the Cambrian, but then started to be outcompeted and had really disappeared by the end of the Permian. Although by the end of the Devonian, they were very, very insignificant. The blue area on the graph then is the Paleozoic fauna. These are defined as brachiopod-rich assemblages. These are the fossils that appeared during what we call the Ordovician radiation, the biodiversification event that happened through the Ordovician period. Bigger scale than the one that happened during the Cambrian, but one that perhaps gets a little overlooked because it was a development of life that already existed. We see like the articulate, the brachiopods, most brachiopods appeared at this time, cephalopods as well. The final group then, shown in the green shading here, is the modern fauna. This is a mollusk-rich assemblage. So things like gastropods, snails, bivalves, echinoids, all appeared at this point in time. You can see that all of these groups actually appeared in the Cambrian, but it's really the point at which they dominate that that really we try and define these groups by. So you can see the modern fauna dominates the Mesozoic and Cenozoic eras. Now along with this changing diversity of these different groups, you can see at various points on this graph we have sudden drops in diversity, sudden drop in the number of marine invertebrate families, numbered from 1 to 5 on this graph. Let's look at each one of these events, because these are our mass extinctions. Okay. A mass extinction is a huge event. Number of things has to happen for it to be a mass extinction. It's not the same as just an extinction of a species. Firstly, it has to be a significant proportion of species. There has to be a loss of species diversity, not an individual species going, but lots of them. Numbers there between 30% and 95% of species becoming extinct. These species need to become extinct in different environments. So marine and terrestrial organisms becoming extinct at the same time. And finally, they have to occur rapidly, just a few million years. Now, for these things to happen, generally, there's got to be more than one physical factor affecting this, more than one cause for an event on this scale. These are the 5 biggies. At the end of the Ordovician, in the late Devonian, at the end of the Permian period, the end of the Triassic period, and the end of the Cretaceous period. These are the ones that are marked up on your version of this graph. You can see that there's no sort of standard spacing. These things don't happen in just a sequence as a result of time. You've got gaps between 51 and 135 million years. This thing isn't if you like, a regular occurrence. So what we need to look at is what actually happened at each of these events. How can we recognise the impact of these 5 mass extinctions? There are several considerations we need to have thought about if we're going to try and explain the cause of a mass extinction. Let's think about the end Cretaceous example. It's the most famous, the most studied, the one that killed the dinosaurs. If we're coming up with a mechanism to cause this mass extinction, we can't have something that perhaps only affects dinosaurs, because lots of other organisms died out at the same time. So any cause that we suggest needs to affect all the known victims. What we can't have, though, is overkill. We can't come up with a mechanism for mass extinction that wipes out life on Earth, because we know that didn't happen. We're literally living proof that life on Earth hasn't been wiped out. We need to consider, is the cause terrestrial, from Earth, or a bit more cosmic, came from outer space? We can also try and consider it as a biological cause, or is it a more abiotic, a physical cause of a geological process? When we're considering any mass extinction, we need to think as well, is it unique? Or is there a common cause to mass extinctions? When we get a particular coming together of events, or is each mass extinction a result of particular conditions that exist at that time? We also need to consider timescales. Now, this can be difficult in geology. When we say instantaneous, is that seconds, minutes, hours, weeks, years? Because they're all going to look fairly similar in the geological record. Interestingly, was it one thing that caused the extinction, or were there several things going or happening simultaneously whose effects multiplied each other? And finally, if we've got marine and terrestrial extinctions occurring together, was that the same cause for both of those extinctions, or was it different? So there's a lot to consider when we're trying to come up with a mechanism for this. And what I'd like us to do is to consider what might actually cause it. Now, there are 4 different ways to kill something. We can cause some trauma, injury. We could poison the organism, give it something that it can't ingest that will cause organ failure. We could suffocate it, starve it from the oxygen it needs. Or we could starve it, to remove its source of nutrition. So, what I'd like you to do is I'd like you to work your way through this list and tick off how each of the causes of mass extinction, or each of the suggested causes of mass extinction down the left-hand side, would actually kill organisms. So how would a meteorite impact actually kill animals and plants? How would volcanism? How would climatic change, which is often given as a cause of mass extinction? How would sea level change or predation, disease or competition actually go about killing these things? Once we've done that, we can then start thinking about whether we can actually test these hypotheses and whether we get a record independent of the actual extinction itself in the geological record. It's all very well to come up with theories like, space aliens hunting the dinosaurs to extinction. Fine, but, where's the evidence for that? Okay. If we don't have those 2 ideas, we don't have those 2 things considered, what we have is a wild guess, not a scientific hypothesis. So, have a go at that, see what you come up with.